do appreciate everybody coming here. I want you to know that the level I'm trying to pitch this at, I wasn't sure who was going to come, so I kind of have something for everybody. Some of us who are true croc aficionados and those who wish they were. But the reason I entitled the talk "The Myth of the Living Fossil" is it gets on two issues that I've been working on simultaneously. One is this idea that crocodilians and crocodiliforms more generally are living fossils, haven't changed since the days of the dinosaurs. Everyone has probably heard that, which it's nonsense. Okay, it is absolute nonsense, and I hope to disavow you of that misappropriation tonight. But it also speaks to ways in which we scientists have misled ourselves by using, even those of us who are working very hard to suppress this preconception, it was still there, it was still latent. And it misled us in some ways by I don't want to use the word biasing, but that actually probably is the correct term, our sampling strategies. And at the end I'm going to show you where I think actually I may have led everyone astray pretty badly. But before I go any further, I want to thank a lot of people. I'm not the only one who's behind this talk. I've got a lot of students, current and past, who have done a lot of work that goes along in this. In particular, I managed to get, at this time, every student I have or I've ever had in one spot. Stephanie Drumheller just graduated last night. She's now Dr. Drumheller Horton. She works on alligator bite marks. She actually got a slaughterhouse to donate cow and pig legs, drove down to St. Augustine, threw them in, and got bite marks from every living crocodilian species, or almost every one. So she would throw them in, let the gator play with it, and then go and get it. And she'll be back. She actually is at the University of Tennessee in Knoxville. She'll be back there, so local flavor. Alan Turner here has really pioneered a lot of our work on sort of the group of crocodiliforms that leads toward modern crocodilians but aren't quite in it. I've got Eric Allen here, who's worked on some of those animals as well. Jennifer Nestler, who's now at Stony Brook, who is at the other end of things. It turns out the Nile crocodile is more than one species. And she was looking at the morphology, trying to see if we can sort those out that way, rather than just looking at molecular markers. And Eric Wilberg was looking at some of these weird marine crocodiliforms. Alex has looked at some of these as well, the Dinosaurs. And Eric was looking more at the Metriorhynchids and the Thalattosuchians, but still, it's all part of a broader issue. And Dan Snyder has also worked on some alligators, including some of the ones that we'll be talking about tomorrow as we kibbutz over what's upstairs. And a couple of other people to thank. Lou Densmore, I cannot thank this guy enough. Lou Densmore founded the modern field of croc phylogenetics. He did the molecular work in the 1980s. And he and I lived in the same state for 9 years, and we finally met in Australia. And he and I have become really close friends and colleagues. He and I both, we don't care what the answer is, we just want to know about the animals. And I've really come to rely on him. And finally, this guy here, John Thorbjarnarson, the greatest croc conservation biologist ever. Okay, he was able to bring together communities of people who might have anything possibly to contribute to the conservation of a species, which is why he had an idiot like me in Cuba dealing with animals that are still using their soft parts. And a couple of years ago, he was in Africa. I was corresponding with him about some subfossils. 2 days later, he went to India and died of malaria. Very premature. We all still miss him. Anyway. With the what? Oh, that's Gary Morgan, who used to be at the University of Florida. He's now at New Mexico Museum of Natural Science in Albuquerque. He's been working with this woman here, Nancy Albury. She's at the University of the Bahamas. And they've got some subfossil Cuban crocodile material in the Bahamas, and they've been working together on some of that stuff. And the reason he's got that shirt is he's got a collection of University of Florida shirts in which the person designing the shirt accidentally put in a crocodile instead of a gator. Usually those shirts last until someone realizes, hey, that's a crocodile, and then it's off the shelves immediately, but he collects them. Oh, one other guy to mention here, Kent Vliet, the world authority on croc behavior. Awesome guy to listen to. All right, now this. I work on both living and fossil crocs, and I don't think I'm the only one in this room who agrees that you can't ignore the fossil and pay only attention to the living, but at the same time you can't ignore, you have to pay attention to both, all right? And the reason you do that is that the modern record, biology these days has a very strong emphasis on what we can get from living species, molecular markers, soft tissues, any kind of that sort of thing. But the modern record is a palimpsest. Okay, now what's a palimpsest? This is a palimpsest. If you go back to the Middle Ages, writing materials were extremely expensive. And so it was very common, instead of taking a new piece of parchment, to take a piece of parchment that had writing on it, scrape the old writing off, and then write over that. And actually, you can see that here, because you can still see traces of the earlier writing in the background with the new writing on top. That's a palimpsest. We actually have some ancient Greek text, including some of Archimedes' works, are only known from palimpsests, where some guy scraped off Archimedes' text and put on something Byzantine era. You know, things like that exist. The modern biota gives us a lot of information, but it overprints its history as it does so. And we can get a lot of that past history from the living species as well, but again, because of the overprinting, it might be biased. The fossil record is incomplete, it is also biased, but in different ways. And we cannot ignore one and pay attention only to the other, because the modern gives us a lot, but it overprints its past. Let me give you a couple of examples. This has nothing to do with crocs, obviously. If we look at the modern vertebrates with jaws, okay, so the chondrichthyes is sharks and rays, osteichthyes is everything else. We are in this, bony fishes, frogs, alligators, birds. But then you've got the jawless fishes down here. There are a lot of anatomical characters that separate the gnathostomes, the jawed vertebrates, from everybody else. There are also a lot of gene duplications, a lot of times where the whole genome was duplicated, and where you'd have one copy of parts of a genome in a lamprey, you'd have 2 or 3 in a jawed vertebrate. And so it was often thought, well, you've got a lot of gene duplication events, you've got a lot of characters, jaws, paired appendages, a cerebellum, things like that. Maybe there's a correlation. Except when you add the fossils, these characters don't just arise at one node. They actually arose stepwise throughout vertebrate phylogeny. All of these things, with the exception of the placoderms, which is probably not monophyletic, are jawless fishes. And where along these lines do any of these genome duplications occur? So that whole genome duplication, massive morphological reorganization correlation completely collapses if you consider the depth of history that we can actually reconstruct if you include the fossils. Okay. Another kind of a simpler example, an alligator and a crocodile. A lot of people say you can tell them apart by looking at the shape of the snout. Gators have a broad snout, alligators have a narrow one. That works if you've got the American alligator and a Nile crocodile. It doesn't pretty much work across the board. One thing that does typically work, as long as you don't have a zoo animal, is occlusion. Okay, the way the teeth come together. Alligators, like this one here, using a turtle as a pillow, the lower teeth occlude lingual to the upper. Basically, there's an overbite. All right. Crocodiles, like this American crocodile here, the teeth interfinger when the jaws are closed. Okay. Now, which one evolved into which? Any guesses? Okay. It turns out they both evolved from something totally different. Basically, the actual ancestral occlusal pattern does not exist in modern crocodilians. You've got a notch between the maxilla here and the premaxilla, and 1 or 2 teeth occlude in that. There's an overbite behind that. Alligators lost the notch, crocodiles lost the overbite. So the actual ancestral condition doesn't even exist in the modern world, and we would never have predicted that just from the living species. Okay, so a simpler example of the same sort of thing. The modern taxa are a palimpsest of their past. This, by the way, is Lydiasuchus, for those who are interested. All right, so we need fossils. They're the only direct evidence we have for past life. The only way we're going to get access to the past directly. We can indirectly approximate it with molecular data, with phylogenetic bracketing and all that stuff, but if we want to actually see it, we need fossils. And as I've just explained to you, what we learn from the modern biota, however rich that is, might overprint what occurred in the past. But fossils by themselves, without that phylogenetic context, are not as informative. We need them in an evolutionary or phylogenetic context. Fossil record is incomplete. You can't just interpret the fossil record literally. Phylogenetic history gives us one way of at least partially correcting for the incompleteness of the fossil record. It's not necessarily the best way to do it, it's not the only way, but it is a powerful way of doing it. Rate calibration is impossible otherwise. You don't want to if you want to use, for example, molecular clocks. People don't actually use clocks anymore, but if you want to use molecular data to tell time, you're basically dealing with rates of evolution. To get rate, you need both time and distance. Molecular data can give you the distance, the fossils give you the time. Fossils do not calibrate rates of evolution. Nodes on trees calibrate rates of evolution. A fossil calibration is an inherently phylogenetic statement. Without a phylogeny, you cannot calibrate rates of evolution. Full stop. Can't do it. All right. I would also say that if you want to look at rates of extinction, people come up with rates of extinction from molecular phylogenies. They shouldn't. I'll explain why in a minute. And if you want to compare different hypotheses, a lot of the so-called molecular morphological conflicts of the past had nothing to do with molecules clashing with morphology. They had everything to do with a phylogeny based on molecular data with something pulled out of a field guide. Okay, something that came out of taxonomy by assertion. That's not really a phylogeny. It was apples to oranges. This way we've got a common language, a common basis of comparison that didn't necessarily exist before. When you analyze morphology properly, most, not all, but most of those conflicts tend to go away. Okay, I'll show you an example here shortly. All right, now why do you want to work on crocodilians? Besides the fact that I like them. First of all, they are better than dinosaurs, objectively. We do not need special effects to see them eat people. And I don't mean leaving somebody out in the desert for vultures. That doesn't count. They live in their own depositional systems. They've got a great fossil record, at least 9-to-1 ratio. It's going to go up because there's some new fossils being described. All right, that's going to actually bump that number up. But we have limited extant diversity, which means we can exhaustively sample the modern species for any kind of data we can get from those. The phylogenies we get from different sources are actually strongly in agreement. There are some conflicts, but for the most part, they tell you the same thing, which gives us confidence that we're getting pretty close to the right answer in most cases. And yeah, there's underappreciated diversity. I'll show you some pictures of that in a minute. They really are kind of neat animals. This is not, by the way, Crocodylia is not an ancient lineage. Crocodylia first appears in the fossil record about 80 to 85 million years ago. By way of comparison, the last common ancestor of chickens and ducks is older than that. The last common ancestor of geckos and other lizards is older than that. Last common ancestor of side-neck and not side-neck turtles is older than that. Last common ancestor of elephants and primates is older than that. So Crocodylia is actually one of the younger clades out there. It's not an ancient clade at all. It's a young clade, very young. All right. But who are they? This is a tree that shows us just the living species, just the living ones. 3 basic clades today. You've got, well, 2 basic and then a couple that we're still trying to figure out. The alligatorids, that's the American alligator here. The caimans, it's a Latin American radiation for the most part. Fossil record complicates it, but for the most part Latin American. This is a dwarf caiman here. Then you get the crocodilids, the true crocodiles. Cuban crocs, Osteolaemus down here, the African dwarf crocodile. This one's getting split into at least 3 species, maybe more. So we've got the crocs, you've got the gators, and then you've got the tube heads. You've got things like the true gharial and the false gharial. This is where things get complicated because the Malayan false gharial morphologically appears to be a crocodilid. But the Indian gharial, based on morphology, is distantly related to any other living croc, but based on molecular data, it's related to Tomistoma. And I'll come back to that point in a minute. And again, this is a group with a great fossil record. This is something that many of you here, I'm sure, have seen. It's the gator from the Gray site, just as an example of great fossils within the clade. And again, underappreciated diversity. A lot of the fossils we get do kind of sort of resemble living crocs. I mean, this one, basically alligator shape. Some differences. It's not exactly the same, but it's close. But then you've got things like this. They're currently called the Pristacampsines. That name's going to change, but the Pristacampsines, these things had serrated, flattened teeth. The claws were more like little hooves, so we call them hoofed crocodiles. They had the same number of fingers and toes, just each one ended in a little hoof. Deep snouts, this one's eating a horse. I'm cheating, that's a primitive horse about the size of a Cocker Spaniel, but you get the idea. We think these things were less aquatic than their modern counterparts, and in the wake of the extinction of big predatory dinosaurs, this might have been one of the groups that was trying to fill that role on land. Didn't do so hot in the northern continents, but South America they did somewhat better. Different group down there. And then we got some that don't make any sense. Murasuchus, this is a caiman. This one's from Venezuela, this one from Argentina. It looks like kind of like a surfboard with eyeballs, and granted, these teeth themselves are actually dentures. They're actually little plaster plugs that somebody wedged in at random intervals without actually recognizing where the alveoli, the tooth sockets were, but it did have lots of very small teeth. And then my personal favorite, Purosaurus. There's a meter stick here for scale, so you get an idea how big it was. There are the eyes, and that is the nose, and that is not broken. Okay? You can literally put your head in this animal's nose and look around, which is a very humbling experience. I've done it. And I have no idea. My best guess is that they were inhaling their prey. Some paca or capybara was wandering by, and that'd be the end of it. That thing is actually big enough to swallow a capybara just through the nose. It wants to snort guinea pigs, hey, whatever. But this particular one's from Brazil. Now, and again, in terms of how good the fossil record is, it's not perfect. There are gaps. We actually understand many of those gaps too. We actually kind of know where the biggest gaps are, and that gives us reason to be very cautious about parts of the tree that we know. But just on this one, this is, at the time I drew it about 2 years ago, every crocodilian species I could think of, where I personally believe it goes phylogenetically, not necessarily where the analysis says it goes. That is what's alive. All right, so if you exclude the fossils, that's how much of the story you're just tossing out. So if you want to look at the whole history of a group, you got to include the fossils, especially if you've got a record this good. So, and actually I got dinged on this on a proposal. I actually got funded on this one. And I always ask, is Anonymous actually here? The guy who reviewed this proposal, is that person in the room, just to make sure? But basically, the guy missed our point. Extinction of most of your in-group is a serious problem. The thing is, everyone's group is majority extinct. The difference is we can sample a lot of that extinction. That's the point I was trying to make. Not, our animals are dead. Well, yeah, but so are yours. The thing is, I can see mine. Okay, that's the whole point. And another example of how the fossil record enriches what we know. What I've shown here, OTU, it's a fancy term called operational taxonomic unit, basically species. Okay, more or less. That's what this curve. This shows the diversity of crocodilians over time. This one shows ratios of oxygen isotopes. This one can be seen as a proxy for climate, basically. As this curve goes up, temperatures around the world get warmer. As it goes down, they get cooler. And what you see is that there's a bimodal distribution in croc diversity. It goes up down here in sort of about 50 million years ago, and then it drops, and then it rises again. It kind of mirrors climate to a certain extent. Climate warms, then it cools, then it gets warmer again. It cools, but at this point we've got a much better fossil record, and plus we've also got the living species now being added into the mix. And so that prevents the curve from going back down again. We think that's what's going on there. But basically, you've got a good tight correlation. So we would expect from this patterns of diversification and extinction to be bimodal, to show either a burst of diversification followed by an extinction and then another burst. Well, not necessarily. Okay, here's a tree right here that shows the living lineages and when these living lineages diverged. And what these curves show is just the number of branches that existed at any given time. And what they show is kind of a slow rate of diversification, and then all of a sudden they really skyrocket as you've got lots of divergence points taken off. Okay, so what this shows is that you've got slow rates of evolution and then a burst of evolution sort of within the past 20 to 30 million, which doesn't match the fossil record. And if you include the fossils, it's not what you get at all. You get fast diversification, then slow, and then fast again. You don't get that bimodality until you include the fossils, which actually makes perfectly intuitive sense if you know the fossil record. Most of these divergence points happen to be fairly recent, but these are speciose clades of closely related species, like within the caimans or the true crocodiles. Most of the deeper branches are older, but there's a lot of diversity that's just no longer around. You cannot get this bimodality without the fossils. You cannot really get extinction rates or multiple levels of diversification without the fossil record. I don't care what people tell you. People will say, I've got a model that can do it, and I'll say, no, you don't. At least not that's useful. So, what are the conflicts? And this is where I'm getting back into the whole myth of the fossil record thing, because in a way I sort of fell into the same trap, even as I was trying desperately to avoid it. These are the living croc group, well, these aren't, but living croc groups. If we look at anatomical or morphological data, gharials is distantly related, and it's a Mesozoic divergence. Late Cretaceous, basically. If you look at molecular data, gharials and Thymistoma are close relatives, and they diverged during the Cenozoic, maybe even during the Neogene. Okay, now this is a really confounding problem, because most of the time when you hear molecules morphology, what you hear is that you've got two animals that look the same. And taxonomists had always said they were closely related, but now molecular data says that they're convergent, they're distantly related, and they diverged way back in the past. It's the opposite here. Here we've got two animals that look the same, but it's the morphologists who are saying, no, they're convergent, and it's a deep divergence. Now, why is this happening? We don't really know, but we can always take heart with the fact that we can keep adding data. Now, with morphology, we have great potential for taxon sampling. We can keep adding fossils. With molecular data, we can keep adding characters, because we can keep adding genes, right, which gives us a lot of characters. But we can't really include molecular data for the vast majority of fossils, right? So we can have two vectors of growth, but they diverge. They don't necessarily intersect very much. And so when I started working on these things in the early 90s, I took a step back, and these were the big conflicts. Well, how old is Crocodylia? How old is some of these other groups? Jawless, how old is Alligator? It turns out, once you analyze morphology using modern methods, the vast majority of these go away. And in fact, most of these had nothing to do with the data and everything to do with how the names were being used. This conflict with Alligator was that people were looking at Alligator as a stem genus, including things that were not descended from the last common ancestor of the living species. Everyone knew that those things in the Eocene had nothing to do with that. But gharials, that problem simply hasn't gone away. And if you look at all the other things where the data sets have always agreed, or where neither set tells you anything, but they agree on not being able to say anything at all, it's even more confounding. So we've really been adding a lot of data in the last couple of decades. If we go back to when Jim Clark did his work in the 80s, this wasn't just within Crocodylia, this is Crocodiliformes. We've added an order of magnitude taxa to the different analyses that are out there. If we look at molecular sequence sampling, we started with 1,300 bases around 2000. Now we've got an order of magnitude more than that, excluding the complete mitochondrial sequences. Okay? And so you've got similar levels of data set increase, and the problem hasn't gone away. All right? And so I have to sit back and say, I've got all these different genes that are being analyzed. They're nuclear, they're mitochondrial, they're all being analyzed in different methods. They're all telling us the same thing. I've got my little data set here all by its lonesome saying something else. I want to be right, obviously, but I also have to think of the great words of Isaac Asimov here. Probably not, just realistically. So what's going on? And there are other things that were kind of letting me know that maybe there was more there than I was realizing. If we take a look at a croc phylogeny and map it out over time, in orange here, here's the modern Malayan false gharial. So these are the Themistomines. There's the Indian gharial and some of its relatives. These are the gavialoids. It's these fossils down here, the so-called Thoracosaurs, that even if you constrain the analysis to give you the molecular result in terms of the relationships, it still gives you the morphological result in terms of divergence time, because these fossils down here in the late Cretaceous and early Cenozoic in the Paleogene are still down here, separating gharials and Thymistoma. But there was something else going on. You got all these Thyracosaurs in the late Cretaceous into the Paleocene, and then you've got other gharials that first appear in the latest Eocene and nothing in between, which was a real issue because this right here, this is the Eocene, and arguably the early to middle Eocene is the best sampled and best represented section time period for crocodilians. If there's going to be if you're a crocodilian group and you existed in the Eocene, you're going to be showing up somewhere because that's the best time to be a croc in terms of being the fossil record. And so we've got this big gap. Maybe that's telling us something. Maybe it's telling us that these things belong over here and these don't, which would mean these aren't actually crocodilians. I don't know. Along with a couple of other things here too. I really don't know. And so we kept adding fossils. And the thing is, we kept adding fossils that looked like gharials on the theory that if we're going to solve the problem, we've got one thing that looks like a gharial, another thing that looks like a gharial, throw everything that looks like a gharial, eventually that'll sort itself out. And you know, some of these things that might as well be the Indian gharial. This one's actually from Java, but still, you get the idea. This one here is actually from Tennessee. So, but I think when I finally realized what was, and actually, by the way, the oldest of those Thyracosaurs is from Tennessee, just so you guys know. The glimmer of where I think things are headed came from animals that looked the opposite of a gharial. Totally other direction morphologically anyway. And here's one of them, Acynodon. Both of them are called Acynodon. This one's from the late Cretaceous this particular one's from France, but it's known from France and Spain. And another one from Italy, Acynodon adriaticus. These things are dead ringers for early alligator relatives, things we call globodontans. They look a lot like things like this. This one's from Canada. This is related to both alligators and caimans. It's a close relative of Alligatoridae. It's got a little short snout, it's got crushing teeth in the back, and Acynodon looked a lot like it. Acynodon is European. All the other early alligatoroids are North American, so maybe these things came from Europe, not North America, which is kind of weird. And they do in fact have, don't worry about the text, they do in fact have a lot of characters that link them to alligators in phylogenetic analyses. But, yeah, in some of these analyses, you know, that they were being done, they were coming up as close to Alligatoridae right here. But I then took a closer look at these fossils, and they didn't make sense as alligatoroids. Okay, for one thing, they don't have a mandibular fenestra, a big hole in the back of the jaw. You can see it here in a caiman. There's some damage here, but this thing really didn't have one. And you look at the others, they just don't have it. That's true for a lot of things that are related to Crocodilia, but outside of it, not true for anything within Crocodilia. All right, and a few other things too. For example, whether or not certain openings in the back of the skull were actually channels and not holes. You know, things that were kind of strange. There were also similarities with these fossils. And when I first started working on these things, this was the only one of them that was known, Hyliacampsa. We've now got this other Hyliacampsid, Eharcodosuchus. They looked a lot like these too. These are not crocodilians. They're related, but they're outside Crocodilia. And they have really big crushing teeth, and they look like little alligators. For example, there's a muscle attachment scar on the underside of the skull that normally forms a low crest. In these things, it's basically a big knob. It's like someone sticking a fist through the quadrate, you know, or the quadratojugal, depending on which bone. You know, it's huge. The maxilla shoots straight back and forms a part of this bone here. This structure here, I'd never heard of that. You get that in Hyliacampsa, you get it in Eharcodosuchus, you get it in Acynodon. And so what we did, and yeah, another thing is, you know, thin crest here, the foramen areum it's a hole that an air-filled tube passes through that in life, or would have, same structure. And even within Acynodon, when it was originally described, the sutures were drawn like this. I went back and saw it myself, and I have a different interpretation of the morphology. And, for example, the prefrontals meet at the midline. A couple of caimans do that, but so does Hyliacampsa. I actually miscoded that the first time I ran my matrix. I went back and looked at the fossil again, and I was wrong. So when we did a couple of things. We added some additional characters. We also added some additional taxa outside Crocodilia. when Acynodon was first shown to be an alligatoroid, they put it in a matrix that had nothing but alligatoroids in it. You can put a duck in that matrix. It will come up as an alligatoroid. You can put yourself in the matrix. You'll come up as an alligator. You have nowhere else to go, right? So we expanded that. And it turns out that Acynodon, first of all, is not monophyletic. The Italian one is more closely related to these than is the French and the Franco-Spanish one. And it really is not it's not even a crocodilian, much less an alligatorid. Okay, so that got me thinking because, this idea that crocs are living fossils, we've already pretty much debunked that, that you go back in time and there's always something that's crocodile-shaped. Okay, but even William Buckland said, no reason to study them. They haven't changed, and that impacts paleo art. This thing down here should not have looked like an American alligator. It actually did look kind of different. And of course, the emphasis is on these big things here and, all these other weird mammals, because that's the really strange thing. If you want a landscape to look primitive, throw an alligator in it. It's like the blue blazer you keep in the back of your closet. If you need to suddenly look like you're dressed up, you throw that on. Same thing. You put in some Spanish moss, some fog, and an alligator, and all of a sudden it looks primeval, even though they really didn't look the same throughout, but they did look similar. And so as a result, we assumed, I realized that there was all this unexpected diversity, but I still, and a lot of us assumed that the ancestral crocodilian would have looked kind of like a modern alligator or crocodile. That was based in part on the fact that if you look at a phylogeny of just a living species, that's how they optimize. Okay, so we're talking about an animal bigger than 2.5 meters as an adult. Basically, it's got a bunch of cone-shaped teeth, reasonably broad, flat snout, ate pretty much whatever it wanted, lived wherever it had enough space and water and food. Okay, not all that sensitive really. Sensitive, but not that much. We assume that would be the ancestral condition. But now let's take a look at some other fossils, and some of these have only been known for no more than 10 years. Okay, the Susisuchids were unknown until 2006. Or actually, wait, 2003 I think is when this one came out. And now no published analysis has drawn them together. They're together, trust me, okay? These look a lot like little miniature alligators. These things were called paralligatorids for a reason. Okay, Shamasuchus, there's other species in there. This tree doesn't show them, but there are some other species as well that look kind of like this. This is actually a different species. The Stomatosuchus, now these ones weren't small, but again, they had that broad U-shaped snout. They had a lot of other features that were alligator-like. Again, a lot of these other things, it's in a topasaurid, but this one is called Alligatorium. All right, now this one is probably not an adult, but that group, none of them got very big. And so actually the ancestral crocodilian, we now think, was small, maybe no bigger than 2 meters, if that. A lot like an early alligator, or alligatoroid anyway, with all these features that we see in those. It didn't look like a modern alligator or crocodile. Now here's the thing, when I was doing my analyses, I excluded a lot of these outgroups because they looked too weird. They looked too much like a little alligator. Obviously I wanted to look for something that looks like a modern croc. And this brings up the issue of something that's a problem to all systematists, rooting. Basically, when the computer programs give you a tree, the tree doesn't necessarily have a time direction right away. You have to add specific outgroups to the analysis to put a root on the tree so that it gives it the time axis. It puts a base on that tree. If our outgroups are telling the tree that the ancestral condition should look like our preconception of an ancestral crocodilian, it's going to root the tree that way. And a lot of features that might actually be ancestral for Crocodylia are going to come up as derived for alligators. Okay? Now this doesn't solve the whole problem. You can't reroute the morphological tree to get the molecular tree. Just can't do that. But it is raising the specter of characters being mispolarized by the way we sample our outgroups. And so when I bring this up to biology groups, I say if it turns out that Gavialis really is close to Tomistoma, it's not because molecular data were better, it's because morphological data were more sensitive to outgroup sampling. And that's not unique to morphological data, dude. All right. And in a way, we sort of misled ourselves away from looking at it by the way we sampled even our in-group, okay? We were looking at these bright, shiny, tube-headed crocodilians thinking the answer would be there when the reality was about to just bite our heads off. You know, and let's go ahead and skip that one. So I think what's going on now is we're sort of getting into what I would call the third generation of the phylogenetic analyses here. Okay, you've got a basic framework established. Jim Clark did this in 1986. Did the first broad analysis of Crocodilomorpha. Here's Crocodylia down here. Hyliacamps is down here. And then we all sort of played riffs off of this. And so for the next 20 years, you know, some of us focused heavily on the crown. I added a lot of characters, a lot of taxa to the crown group to figure out what's going on. We had people looking at the Dinosaurs, Alex, for example, and Stefan Jouve and a few others who really hammered that group home. We had several of our South American colleagues who really, you know, especially with some new spectacular discoveries of these Notosuchians. Turns out these things are probably closely related. Others working on the Metriorhynchids, including my student Eric Wilberg. We added taxa and characters, but we didn't really think about what's going on in between, right? What have I learned within Crocodylia that would inform Mark Young, who's working on Metriorhynchids? You know, what has Diego Pohl learned that would inform me? That really never crossed our minds. And so what we now need to do is go back and resynthesize. Now here's an example of where I think that might have actually caused an actual wrong result. This came out early last year, Aegisuchus. It's a cool fossil, and I'm going to criticize it, but I want to say this really was a beautiful paper. Okay, I'm going to criticize an aspect of it, but the bulk of that paper was really quite good and had some excellent information. But the phylogeny was problematic. In both of the analyses, they had Aegisuchus and something else as the closest relatives of Crocodylia, which raised all kinds of interesting problems. This thing's from the southern hemisphere. We always assumed Crocodylians initially came from the northern hemisphere. What's going on? Well, take a look at the analyses. The first one they did was based on a matrix that was initially designed to work out some of these really early crocodiliforms, things like Notosuchians. It didn't have a whole lot of information for what was going on up in this part of the tree because the people doing the analysis weren't interested in that. They were interested in stuff further down. Well, if you put something in the matrix that's close to the crown and there's not a lot of information about the crown, guess where it's going to come up? Next to the crown. The other analysis, they said Delfino et al. Actually, that should be Brochu, but that matrix there was optimized for the crown. Not a whole lot of information in that for what's going on downstream of that. There's not a lot of character information for down here. If you put something in that that's close to the crown but not within it, it's going to come up pretty damn close to the crown. It might even be next to it, even if it doesn't belong there. The reason these results obtained wasn't because of any, you know, wrong thinking. It's just that there really is no matrix out there that is optimized for that part of the tree. That section of the tree between the crown and the basalmost Neosuchians, which is part of what I'm trying to do now. That's actually a big part of my research now, is trying to fill in that gap. Because there really is no way to fill that in, and so for the time being, it's really hard to say where these things go phylogenetically. Okay, we may know they're going to be somewhere between the crown and something down here, but beyond that, it's hard to say. And yeah, who's to blame? Who caused this problem? We can actually identify that person. He's right there. So that was during my Kurt Cobain phase. Anyway, so now we need to take what I call the third generation. And actually, if you look at most other groups that have been analyzed phylogenetically, you see the same sort of ontogeny of phylogeny, the same sort of history of study where someone takes a step back. With dinosaurs, you had Jacques Gaudier put together that first broad-scale analysis, and Paul Serino on the Ornithischians. And then you had Tom Holtz, and you had Pete Makovicki, and you had Luis Chiappe and Kathy Forster and all these others jump in and work on different groups within Dinosauria. Now what's happening is you've got these other groups stepping back and combining the matrices, which is not a trivial thing to do, believe me, and coming up with a synthetic whole that actually is able to test those earlier phylogenies in ways that we couldn't before. And I think you find that's true for most groups, and I think that's where we're headed with Crocodylia. And I think eventually we will solve that Gharials problem that way. So just some concluding remarks. Both modern and fossil biotas, it's going to be biased no matter what, but they're biased in different ways. Either you're erasing the past, or you're getting a past that's not accurate. You're always going to get diversification patterns that are unimodal. Okay, you have to include fossils if you want to get rates of evolution accurately or anything else. So, I think we are approaching resolution of the gharial problem. I think we may have mischaracterized the ancestral croc. Even those of us who were working very hard to not make assumptions were making assumptions we weren't even aware we were making, and this may have been to our detriment. And a lot of people to thank, and thank you for coming here. I appreciate it.